Judging by the title, this episode is a joke, and not a very clever one. According to the widely accepted Big Bang theory, our universe emerged from an extreme state of physical vacuum. In this state, neither time nor space existed, or they were fused into a single space-time. All fundamental physical interactions were unified. Later, they separated and acquired independent existence. First gravity, then the strong interaction, and only then the weak and electromagnetic interactions. The moment preceding these changes is conventionally referred to as zero time. However, this is a pure convention, a tribute to mathematical formalism. According to the standard theory, the continuous flow of time began only after one gravity gained its independent existence. This moment is usually attributed a value called Planck time. Modern physical theories simply cannot meaningfully work with shorter time intervals. It is believed that this requires a quantum theory of gravity, which has not yet been created. An indispensable part of the standard cosmological theory is the concept of inflation. After inflation ended, gravity took over, and the universe continued its expansion. This evolution stretched over 9 billion years, after which another anti-gravitational field of unknown nature, called dark energy, came into play. It again put the universe into an expansion mode, which seems to be preserved in future times. The inflationary interpretation of the Big Bang was first proposed about 30 years ago and has been refined many times since then. Soon after its appearance, the inflationary model did not contradict the idea of the multiple births of new universes. Indeed, quantum fluctuations, similar to those that gave rise to our world, can arise in any number if suitable conditions exist. It is possible that our universe emerged from a fluctuation zone formed in a precursor world. Similarly, it can be assumed that someday and somewhere in our own universe, a fluctuation will form that will give birth to a completely new young universe, also capable of cosmological expansion. There are cosmological models in which such daughter universes continuously arise, separated from each other by universes with different structures. Competing theories and M-theory. Soon, competitors to the inflationary Big Bang model appeared. They did not gain widespread support but had and still have their followers. The ekpyrotic and cyclic theory is not the first among them, and certainly not the last. However, to date, it is more developed than the others and better explains the observed properties of our world. It has several versions, some of which are based on string theory and multidimensional spaces. The most advanced variant of string theory is known as M-theory. It asserts that the physical world has 11 dimensions, 10 spatial and 1 temporal. Within it, spaces of smaller dimensions called branes float. Our universe is simply one of these branes, possessing 3 spatial dimensions. It is filled with various quantum particles, electrons, quarks, photons, and so on, which are actually open, vibrating strings with a single spatial dimension, length. The ends of each string are firmly fixed within the 3-dimensional brane, and the string cannot leave the brane. However, there are also closed strings that can migrate beyond the branes. These are gravitons, the quanta of the gravitational field. The cyclic theory's explanation of past and future. How does the cyclic theory explain the past and future of the universe? Let's look at the current epoch. Dark energy currently holds the primary influence, causing the universe to expand exponentially, periodically doubling in size. As a result, the density of matter and radiation constantly decreases, for gravitational curvature of space weakens, and its geometry becomes increasingly flat. Over the next trillion years, the universe's size will double about 100 times, and it will transform into a practically empty world, completely devoid of material structures. The collision of branes. Another three-dimensional brane is located near us, separated by a negligible distance in the fourth dimension. It also undergoes similar exponential stretching and flattening. All this time, the distance between the branes practically does not change. Then, these parallel branes begin to approach each other. They are pushed together by a force field whose energy depends on the distance between the branes. Currently, the energy density of such a field is positive. Consequently, it is this field that provides the effect explained by the presence of dark energy. However, this parameter gradually decreases and will fall to zero in 1 trillion years. Both branes will still continue to expand, but at a very slow pace. Therefore, in our world, the density of particles and radiation will remain almost zero, and the geometry 5 flat. A new cycle begins, but the end of the old story is just a prelude to the next cycle. The branes move towards each other and eventually collide. At this stage, the energy density of the interbrane 6 field drops below zero, and it begins to act like gravity. Recall that gravity has negative potential energy. After the collision, in these zones, the lion's share of the kinetic energy released upon impact is liberated. As a result, it is there that most hot plasma, with a temperature of around 1023 degrees, is generated. These regions become local gravitational nodes and turn into the seeds of future galaxies. Cosmological inflation revisited. Finally, let's understand what cosmological inflation is. According to the inflationary model, soon after its birth, the universe expanded exponentially for a very short time, repeatedly doubling its size. Consequently, in many scenarios, inflation was triggered by an anti-gravitational quantum scalar field whose energy density gradually decreased and eventually reached a minimum. Before this happened, the field rapidly transformed into a hot plasma consisting of free quarks, gluons, leptons, and high-energy particles.